So thank you very much for having me and also coming to my talk. So this is joint work with the Young-woo Ko at Hanyang University in Korea and Wei-jae Jung at Stanford. So Young-woo couldn't join us because it's 2:30 a.m. in Korea, and so I thought that Wei-jae is going to come and answer all hard questions, but somehow I'm not seeing him. But please give me any questions. All right, so in this paper we actually study like really simple game. So this is like static complete information game, and we are only going after the Nash equilibrium. So like let me just begin by just telling you what the game is. All right, so there are I players. So there are I players. So from 1 to I. And each player chooses a random variable or a distribution function subject to a set of moment conditions. So here, each player's strategy is a distribution, but there's a constraint, and the constraint is that the distribution, so each player can choose any distribution whose first moment is less than M1, second moment is less than M2, and up to moment N. And then given the distributions, then now there's going to be realizations, and the player who produces the highest realization is going to win. So this is just a contest, and each player is going to maximize the probability of winning. Okay, so in terms of distributions, so this is each player's payoff, and so the way you read this is that so if your realization is X, you are going to win if and only if all other players' realizations are less than X. So then this is each player's payoff. And so in this paper, we are going to focus on the symmetric environment where all the players face the same set of moment constraints. So we are also going to focus on symmetric Nash equilibrium. And so as usual, F star is a symmetric equilibrium if it is a best response to itself. So in other words, F star is an equilibrium if F star maximizes an individual player's payoff subject to among those distributions that satisfy the moment conditions, conditional on the event that all other players play F star. So this is a game, and we just want to analyze this game. So and then why? So here are some economy applications. So in I/O, so there's this classical distinction between vertical differentiation and horizontal differentiation. So the vertical represents the overall quality which all consumers agree on, while horizontal represents and captures the preference diversity. So you may like a particular color. I may not like that color. So we have different preferences, and that's being captured by horizontal. So now imagine that you are designing a product, meaning that you are thinking about what kind of product to produce. Now you need to think about both of these aspects, the vertical and horizontal. So how can you do that? Well, you can do such an exercise in the hoteling framework. But this is ours. Our modeling is another way to do such an exercise because naturally, this vertical dimension corresponds to the mean of the distribution, so the first moment, while the horizontal dimension corresponds to the variance, the second moment. And so to give you some more concrete picture, so let's look at these two different birthday cakes. So the one on the left is a class cake. So I believe that most people like this, but it's unlikely that you get excited about this. But the one on the right, some people are going to really love it. Like my kids really, my sons really like this sort of cake. But someone, if you are a very serious person, you think that this is, you just don't like this. You hate it. Okay. Now imagine that you are a baker, and you are thinking about given some resources, given your skills, you are thinking about what kind of cake to produce. Now you need to think about such consumer reactions. And so our game provides, I believe, a flexible framework to think about such a trade-off. Okay, and here is another, so related application is research contest in which each team needs to decide how ambitious they want to be given their limited resources. Okay, and also finally, in many sports, so you need to decide, you need to think about how well you can play. Not only that, but also you also need to decide how much risk to take. So imagine that you somehow, I don't think it's going to happen to any of us, but imagine that you become a professional tennis player. Okay, and if you know tennis, so suppose that somehow, you met a very nice tennis player, John Isner. And well, you know that you can win as long as you can handle his serves and also consistently return the ball. But if you are going to play against players like Federer, Nadal, Djokovic, you know that it's just not enough to play consistently. You should try something big and risky to have any chance. And thinking about such a strategy, given your athletic abilities, it's like designing a distribution under certain constraint. So here's another example. So suppose that you are going to become national, the coach of the national soccer team for your country, and now you have a bunch of players, and they have different talents. So now you need to construct your own team. So if you are South Korean, now you know that you need to include this guy, the Kyungmin Song, no matter what, because he's just absolutely the best player. But you are going to face a trade-off between a more experienced player and a relatively young and rising player. Okay, so now thinking about thinking about like what kind of team you want to construct is like designing a random variable given under certain constraint. So our framework also provides a way to think about these sports, right? Okay, so there's one paper which also considers the general moment conditions, and that's this paper by 6 authors, and they study the monopoly pricing problem where the nature chooses a distribution subject to certain moment conditions in order to minimize the seller's profit. And so this is actually a great paper, and we learn a lot from this paper, but conceptually, their interpretation of moment conditions is that the seller has partial, imperfect knowledge about the underlying demand or the distribution. While our interpretation is that we just take these moment constraints as direct technological constraints. And so there's also obvious connection to the literature on information design and also the literature on contest. And so our innovation or our contribution is to incorporate general moment conditions into the problem. And the difference from the existing studies in information design and contest is going to get clear as we go on. All right, so I already described the game in full detail. So let me just introduce one piece. So again, there are I players. Each player chooses a distribution subject to moment conditions, and the payoff is just the probability of winning for each guy. And we are going after a symmetric equilibrium. And let me just introduce one piece of notation. So we are going to use this calligraphic f of m to represent to denote the set of all distributions that satisfy a set of the moment constraint. So this f of m is going to be the strategy set for each player from now on. Right, so now let me begin with a very general result that shows that an equilibrium always exists. And so obviously this is not interesting by itself, but at least it shows that our game has a nice structure, and also there's something to characterize. And so let me not get into the details, and let me just mention that this is a discontinuous game because players can choose any distributions, including the ones with atoms. But we still can get the general equilibrium existence using the Billy-Rennie's the results, which turn out to apply beautifully to our game. Okay, so now, we have the existence. So let's not worry about.
Do you get lots of equilibria, or any idea of the multiplicity?
Very good question. I think that we actually have unique equilibrium for all, for all parameter values, but we haven't been able to formally prove. So later, we can actually talk about this more. But for simple problems where there are 2 or 3 constraints, we know that the equilibrium is unique. But so there's some technical issue. So, but I believe that we will be able to get the result. But we just don't know how yet. But
you mean, quick question. So when you say uniqueness, you mean symmetric equilibrium? Or
yes.
Okay.
So we are only looking at the symmetric equilibrium. And so I will also talk about the asymmetric environment a little bit, toward the end, and we can talk more about it.
Okay, thank you.
All right. So the real case. So let's think about the simplest environment where there is only one constraint on the first moment. Okay. So this means that each player can choose any distribution as long as the mean is less than or equal to M1. Okay, so this is the simplest environment. And here this proposition says that it is the unique equilibrium that f star to the I minus 1 is linear and the support is convex starting from 0. And I wrote this proposition this way only to highlight this linearity. I can actually show you the curve solution. So there are 2 unknowns, lambda 1 and x upper bar. So we need 2 equations. And the first equation is simply that this f star is the distribution function. So at the upper bound, x upper bar, it must be equal to 1. So this gives us one equation. The second equation is that the first moment constraint. And that first moment constraint needs to bind. So this means that we're given this f star. If you calculate the first moment, it must be equal to m1. So here are 2 equations, and this is actually very simple system of equations. And once you solve this, we get this Kerr-Pong solution. And so again, here the key is this linearity. So why f star to the I minus 1 must be linear. And in short, this is because each player's optimal solution can be characterized through concavication. But let me give you a more detailed argument because I think this part is good. So first, this f star to the I minus 1, so what is this? Well, recall that this actually appears in the individual player's problem this way. So this was the probability that all other players' realizations are less than x, condition the event that all of them use f star. So notice that this f star to the I minus 1 essentially plays a role as the value function to each individual player. Okay. Now, and the distribution you are choosing is this fi. Now suppose that this f star to the I minus 1 is strictly concave. So this is a figure over its support. So it's concave. Now, so this is simple, thing you learn in first year micro. So you can apply the density inequality, or you can, if you want, you can also apply concavication. Either way, so we know that the player does not want any dispersion. So the optimal strategy for the player is the degenerate distribution at M1. But we know that this given strategy F star is not a degenerate distribution, because if it was the degenerate distribution, it must have not been this concave. So we know that in equilibrium, this cannot be the case. What about if it's convex? So what about if it's strictly convex? Again, you can apply the density inequality, or you can also do concavication. So you just draw this straight line. And then now we know that the optimal strategy is the binary distribution that puts all mass on two extreme points, 0 and x upper bar. So again, this this is just standard concavication. But again, we know that this given distribution f star is not a binary distribution, so this also cannot be the case in equilibrium. In fact, these two arguments, you can apply these two arguments to locally to every subinterval. So then the only thing that survives is this linear. So this f star to the I minus 1 must be linear over its support. And a more direct intuition is that, well, if this is the value function is linear, now you are actually indifferent over a set of distributions. So in fact, you are indifferent over all distributions with mean M1 and the support smaller than the interval from 0 to x upper bar. So again, you are looking for an equilibrium. So this is actually pure strategy equilibrium, but you can actually think about this matching pennies and mixed strategy equilibrium in matching pennies. So this becomes an equilibrium because I have many best responses, but f star is one of those best responses. And if all other players play f star, then again I have many best responses. So it's overall it is the equilibrium that all of us play f star. So that's why this linearity appears in the previous proposition. Okay, good. So this is full characterization for the case where there is the constraint only on the first moment. But in fact, this is actually relatively well-known result in information design. So this is not really our contribution. Our contribution is exactly that we go beyond this first moment problem. Okay, so let's think about the second simplistic environment where there are constraints also on the second moment. So again, each player can choose any distribution whose first moment is less than or equal to M1, and second moment is less than or equal to M2. Now, so one thing which is clear is that if M2 is sufficiently large, then the second moment constraint is going to be irrelevant. Okay, so in fact, this proposition shows that where the previous f star, which we characterize, is going to continue to be the unique equilibrium, and the second moment constraint doesn't matter if and only if M2 exceeds a certain threshold. So in fact, this is very intuitive result. In fact, the only thing we need to do for this result is to calculate. So this was the equivalent distribution from the previous slide, and I just need to calculate its second moment. So M2 upper bar is the second moment of the distribution I found before. And if this given M2 is larger than M2 upper bar, that means that the equilibrium we had already before is going to be an equilibrium in this environment because the second moment constraint is not going to bind. Okay. Again, so far, there's nothing like new. Well, the real question is what has to happen if M2 is less than M2 upper bar so that the second moment constraint need to bind. Okay, now second moment constraint is going to play a real role here. One observation is that now we know that f star to the I minus 1 should be strictly convex. Why? Well, suppose that it's convex, as like here, then the same argument as before applies. So your optimal your best response is going to be a degenerate distribution, but f star is not a degenerate distribution, so it cannot be an equilibrium. And it also cannot be linear because, again, if it is linear, we already saw that it's going to violate the second moment constraint. So it also cannot be the case. So this f star to the I minus 1 not need to be convex. And if you think about it, actually it makes sense because we are looking at the case where the players don't have enough second moment. So that means that they don't have enough capacity to disperse their values. So if the value function is convex, then you want to disperse as much as you can. But there's a constraint on the second moment. So this means that even though the value function is strictly convex, you are not going to choose, so going back, even though the value function is strictly convex, well, you won't be able to choose this binary distribution because that just is not available. That's not feasible. Okay? Because again, you know, there's a constraint on the second moment, so you cannot, there's a limit to which you can disperse the values. So even though this value function is convex, still you might actually play some nice strategy and we can get an equilibrium there. Well,
Teddy, just a clarification. So are you also ruling out sort of any portion, you know, couldn't it be linear on a subset of the support?
So good point. And so you can actually apply these arguments locally to every subinterval. So whenever you have, you know, we have linearity or concavity, you know, you can actually apply this argument. But
I saw that in the previous case, but now sort of the constraint is the second moment, right? Not the first moment. So
so good, very good point. But you know, one thing I can tell you is that so our proof actually does not, you know, rely on such a local argument. So things are gonna be fine. I just wanna, you know, here I just wanna give some intuition about why linearity is not going to work anymore. So that's the most important part I want you to actually get from here. So it's less about convexity. Okay, it's more about that linearity, which worked very well before, is not going to work anymore. Okay.
So Teddy, so this is Yanku. I thought that with the variance constraint in Carrasco-Error and even actually in the old SCARF inventory management, robust inventory management problem, this value function turns out to be quadratic. Is that the case?
That's next slide. So I guess this is not a surprise to you, but this was the sort of surprise to me. And also, you know, as you must know, that there's a good reason for that, and that's actually what I want to move on. So here I said that it must be convex, and the question is how much convexity. Okay, and if you are familiar with this sort of problem with the general moment conditions like Yanku, you must already have some idea about, you know, what we are going to get, and what you know, our contribution is that so first, you know, use that result, and then, you know, exactly pin down the equilibrium. So that's exactly what he did in this paper. Okay, so as Yanku already said, that so the question is how much convexity we need to have. And this proposition shows that, well, that's exactly up to the point where this f star to the I minus 1, the value function, can be expressed as a quadratic function of x. Okay. In fact, we can combine this with the previous proposition, then we get the following result. So you give me any constraint on the first and second moment. So give any strictly positive two-dimensional vector m. So we have m1 and m2. There exists a unique equilibrium in which this f star to the I minus 1 can be expressed as a polynomial function with degree less than or equal to 2. So the first proposition I show you with the first moment is only the case where this lambda 2 is equal to 0. Then we have the linearity. And if, as I just showed, if m2 is less than m2 upper bar, now this lambda 2 must be strictly positive. So we are going to have the nice quadratic function. Why? Okay. So again, if you're familiar with this, you know, the programming with the general moment conditions, you already must have some good idea. But here's the intuition. So just think about the programming problem on the moment conditions. So suppose that the value function is ux, and you are choosing a distribution to maximize your expected payoff subject to these two moment constraints. And if you just write the Lagrangian function, it's going to be simply this, and plus lambda 1 Lagrangian multiplier, and times m1 minus the first moment, plus lambda 2 and m2 minus the second moment. So this is the completely standard way. And then if you arrange terms, you combine these three terms, then we get this expression. Okay, and this lambda 1 times m1 plus lambda 2 times m2 has nothing to do with f. So now we have only this term. And notice that if ux is a quadratic function, in particular, if ux is equal to lambda 1 times x plus lambda 2 times x2, that means that this term is going to be equal to 0. So what does this mean? Well, you are actually, your choice of f doesn't really matter. This actually implies that you are going to be indifferent over a set of distributions. So in some sense, if there's a planner, the planner can, ask you to choose, a particular distribution because you are indifferent. You don't care about, your particular choice. Okay. And again, as before, this is the property we need for equilibrium. And this is why this f star to the I minus 1, this value function must be expressible as a quadratic function or a polynomial.
So you have argued existence. Does this argument give a hint about uniqueness also?
So there are two things. So that our existence argument doesn't imply the uniqueness, but we have the existence, right? And then in fact, for this case, we actually can get a curved form solution.
What?
We can get a closed form solution. So we can so you will see it's going to come in 2 slides. No, actually 1 slide. Sorry, this next slide. Okay, so this is our result, and based on this, we can provide a full characterization. So for each M1, so let's fix M1, or you can normalize M1. Then there are 3 different cases, depending on M2. So if M2 is sufficiently large, in particular, M2 is above N2 upper bar, which is given by this, then only the first moment constraint is going to bind. And this is the case the first case I talked about. So this is the case where f star to the I minus 1 must be, so there's a typo, so all of these guys need to be f star to the I minus 1. So this was the case where f star to the I minus 1 must be linear. But if you go below M2 upper bar, now the second moment constraint is going to bind. So as you see here, lambda 2 is positive. And over some interval, so if M2 belongs to this middle interval, now both constraints are going to bind. So both lambda 1 and lambda 2 are going to be strictly positive. If M2 is sufficiently small, that means that the second moment is really scarce resource. In that case, the first, sometimes players actually, players don't really care much about the first moment. So that's the case where the first moment constraint does not bind, and we are going to have only the case where lambda 2 is strictly positive. So based on this, so this is the curved form solution for the first case when M2 is sufficiently large. This is a curved form solution for the case where when the M2 is sufficiently small. And for the middle case, so this case is much more complicated, but I can actually give you a curved form solution for the case where there are 2 players. So if I is equal to 2, so there are 2 players, then this is a curved form solution. So this is upper bound of the support, and the quiz is lambda 1 and lambda 2. And so things get more complicated. But we have to, and this solution looks very complicated, but this is nice in the sense that it actually connects all the cases continuously and nicely.
Okay, excuse me. Take case 1, the easy case. The argument you gave on the page, can you go back 2 pages? You gave an argument for existence by showing indifference. Yes.
Yes.
That argument. Let's just look at case 1, not 2 and 3. If I look at that argument of indifference, it shows me existence, but I don't see why it also proves uniqueness of equilibrium. Is that supposed to be obvious, or is there another argument?
No, it's not obvious. So if you, but
just for case 1.
If you wait for 2 or 3 slides, I can actually answer that better. So please.
Yeah. Okay. Fine.
Okay. So I actually didn't prove anything for this case because I'm going to actually give you the result for the general case. Okay, and that's going to come into this slide. All right, so let me just some figures. So let me just show you how things, how the equivalent distribution moves as we change M2. So this is the case where there are two players. So I is equal to 2. Then, so recall that, so we had this F star to the I minus 1. Oh, sorry. So F star to the I minus 1, and that's equal to just F star. So when there are two players, F star to the I minus 1 is equal to just F star. And let's normalize M1 to 1. So then if M2 is, so in this case, M2 is greater than or equal to 4 over 3, so it's sufficiently large, then only the first moment constraint binds. In this case, the equilibrium F star is linear. If you go below 4 over 3, so for example, 59 divided by 48, now lambda 2 is going to be positive. So the second moment constraint is also going to bind. Now we have a quadratic function. Okay, and this is the equilibrium distribution. But still, this quadratic function is very close to the linear function. But if you keep decreasing M2, then it becomes more clear, the quadratic function, and it's moving to the left. Okay. Well, so far I've been talking about the case where there are only two constraints. What about in general? So what can you say for the general case with more than two constraints? In fact, it turns out that all the properties I've been talking about continue to hold in the general case with arbitrary moment constraint. So this is the result. So you give me any vector. So this n is the number of constraints, but it can be any natural number. So you give me any vector, strictly positive vector m, then F star is on symmetric equilibrium if and only if there exists a scalar x upper bar. Of course, this is the upper bound of the support, and a non-negative n-dimensional vector lambda that have the following three properties. First, the support must be convex starting from 0. I guess this is not surprising result. And the second, now, because there are n constraints, this F star to the I minus 1 should be expressible as a polynomial function with degree less than or equal to n. And these lambdas are the coefficients of this polynomial function. And so finally, this is the usual complementary length. So for each k, for each moment, either the constraint is going to bind or the Lagrangian multiplier, lambda k, is going to be equal to 0. And so we already talked about, so I didn't really talk much about this, the first one, but this is, I guess this is intuitive. And I already talked about this polynomial representation, and this is the same reason. And complementary slackness, I guess, everyone is familiar with this, okay? So in some sense, it's not really surprising that each of these properties is necessary. But this condition is saying that, well, that's actually necessary and sufficient, okay? So the sufficiency proof is actually very easy and simple, and I can actually do it on one slide, and I think, everyone actually can follow. So let me actually give you the full argument.
Sorry for interrupting. Just want to let you know you have about 10 minutes.
All right.
We're a bit late. Yeah, and there's a question in Q&A.
Oh.
Can I read it out and you decide you want to answer now or maybe postpone to the end? How do you think about the disparity between the objective function and the choice set? You win by having the highest X realization, but the choice set is given by a finite number of moment conditions. I believe such disparity is crucial for getting elegant solution. Do you know anything beyond the case of
sorry, so can I actually read so it's actually a long question? So
yeah, you can leave it to the end. Just want to let you know. Yeah, go ahead, please.
But somehow I cannot actually see my Q&A, the button. But
go ahead. I'll maybe read again by the end of the talk.
All right, thank you. So this is, by the way, this is a necessary sufficient condition. And using this for the case where there are two constraints, we can actually conclude that what you found is the unique equilibrium. Okay. All right. So now, as I promised, So let me give you the full proof for sufficiency. It's actually very straightforward. It's very easy, surprisingly simple. So the only thing we need to show is that, everyone playing F star is an equilibrium. So for that, the only thing I need to show is that conditional on that the other players play F star. No, if individual player prefers F star to any other F that belongs to this strategy set, then we know that this is an equilibrium. So the only thing we need to show is this UF star F star is greater than or equal to UF F star for all F that belongs to this set. Okay. Now looking at this F star, so this is equilibrium payoff. Equilibrium payoff can be written this way. Again, this is, we talked about this. Now, where the support of F star is from 0 to X upper bar, so we can replace this infinity with X upper bar. Okay, so this is the property 1. Now, this F star to the I minus 1, where we know that it can be represented as a polynomial function. Over the support, this F star to the I minus 1 is exactly the same as this polynomial function. So I can replace this F star to the I minus 1 with this polynomial function over this support. Okay, I use the second property. And the final equality is just complementary slackness. For each, so for example, like lambda 1 times first moment must be equal to lambda 1 times m1. And we can do this for each moment. So that's why we have this equality. Okay. Now looking at F, where this is the player's payoff when he plays F. So now again, where we know that this F star to the I minus 1 is coincide with this polynomial function over the support. But if you go beyond the support, where you can the value is going to be equal to 1, so we can replace this F star to the I minus 1 with this function. This is just we just use the fact that the distribution function cannot go above 1. Okay. If we take out this minimum operator, now we get this inequality. And now we're, so looking at this term, we know that each lambda k is positive, no negative. And because this F belongs to this set, where its first moment must be less than or equal to m1. And second moment must be less than or equal to m2. And you do this for each moment, then we get this inequality. And we just proved that UF star F star is larger than or equal to UF F star for all F that belong to this set Fm. And this is the sufficiency proof. Okay. Again, so this is a necessary and sufficient condition. So we can, from now on, we can analyze any problem with arbitrary moment constraint. Okay. So what about if there are 3 moment constraints where, and for simplicity, suppose that I is equal to 2. So there are 2 players. And so each lambda k can be either 0 or positive. But at least one of them must be strictly positive. So total, we have these 7 cases. And for each case, you can construct the equilibrium distribution, and then you can also find the range in which that is actually the equilibrium. Okay. So for example, so in the third case, where this is the case where only the third moment is binding, and then just using the fact that this and so there are 2 unknowns, lambda 3 and X upper bar, and there are 2 equations, then you can construct this equilibrium distribution. Now, once you have the equilibrium distribution, you calculate the first moment and the second moment. And we know that if this equilibrium works, as long as m1 is larger than this first moment and m2 is larger than this second moment. So in this way, we can actually cover every case. Then this is the full characterization. So here I normalized m1 to 1. So I normalize the first moment. And on the x-axis, I have the second moment. On the y-axis, I have third moment. Okay. And this figure shows, on each point, in which case is going to arise. So for example, if here, So this is when both M2 and M3 are sufficiently large. In this case, only the first moment constraint is going to bind, which makes sense. And looking at, for example, here, so this is when M3 is relatively small, while M2 is sufficiently large. In this case, only lambda 3 is going to be positive. This black area is where all three constraints are binding. And this looks like a curve or line, and it's not. This is just so thin, this area is so thin, so it just looks like a line, but this is an area. But it turns out this area turns out to be actually very, very small. Okay. All right, so this is full characterization for the case where there are three constraints. Now, you must have already figured out that things, this number of cases increases exponentially fast as you add more constraints. Okay, so in fact, the number of total cases is going to be 2 to the n minus 1. So we actually start with 3 moments, but turns out that there is actually one general case which we can say actually a lot about. That is when...
Teddy, there were some questions, so you might want to wrap up so we have time to ask you the questions.
Okay, so this is actually the last result I want to talk about. So let me finish this and then let me go to the Q&A. All right, so I think this is by itself, this is interesting result. So here this is what it says. So give me any moment constraint M, then if I, the number of players is sufficiently large, in other words, competition is very intense, then in equilibrium, only the last moment condition is going to bind. So all other moments don't matter. Turns out that only the last moment, the nth moment, is going to bind. But that's the case where only one lambda is positive, so we can actually get a Crawford solution, which is this. Okay, and technically, you can get these results just by calculating the case moment from this distribution. If you do some calculus, then it turns out that this is a case moment. And looking at this, in the numerator, I have I to the k over n. In the denominator, I have I to the 1. So if k is less than 1, k is less than n, then as I goes to infinity, this term is going to go to 0. So that means that all other constraints before n are not going to bind. Okay, and so intuition is intuitively, this is because, so when there are sufficiently many players, you know that it's very hard to win. And this is the case, this is when you really want to disperse your values. Okay, but the higher moment is the one that actually constrains the dispersion more. So that's why only the last moment is going to bind. Okay, right. So I have something a bit more, but this is it. So we are actually working on several things. So first, we are looking at the asymmetric environment. So we can't say too much about the asymmetric case, but I know that we do know that we can provide nice characterization for the case where there are 2 players. And there are also other things we are actually trying to do in this paper. All right, so let me answer the questions. Sorry for the delay.
So Tony, since we're running out of time, so I suggest that we end the formal session, but if you can stick around for a few more minutes, then the questioning Q&A.
All right, thanks very much.
For the rest of you, we will reconvene at 2:30 for the second half of the afternoon session. Okay?